In this example, I apply a 300 Newton force at point A at a 25-degree angle from the horizontal, and I want to figure out the moment that this 300 Newton force produces about point D, which is all the way up here. I also want to figure out what the minimum force I can apply at B is that will produce the same moment about point D that this 300 Newton force produces. So first, I'm going to start by breaking up this 300 newtons into my x and my y components. So when I do this, I have a 300 Newton force. And I know that this is 25 degrees. So this is also 25 degrees. Okay, so I can break this up rather easily. I can say, okay, this is going to be equal to 300 times the cosine of 25. If we go up, this is going to be 300 times the sine. It's getting a little messy, but 300 times the sine of 25. Okay, so if I go to this right here and I say, all right, let's apply it at point A, we know that this will be 300 times the sine of 25. This one right here will be 300 times the cosine of 25. All right, so now let's sum our moments about point D. So the moments that we have about point D are going to be the moments of each of these forces. So what we're first going to do, let's look at going clockwise. So we're going to go clockwise. The two forces that I have are this 300 times the sine of 25. Well, first thing I'm going to do, I'm going to move this so it is aligned with point D. When I align it with point D, I easily see that my perpendicular distance is this 100 millimeters. So, and after I do that, I pin my problem at point D and I rotate the entire thing. When I rotate this entire thing, my vector is going to spin, and when it spins, we're going in this direction. It's going to spin, and the head of my vector is going to lead the way. So that means it needs to be positive. So I'm going to have 300 times the sine of 25. The perpendicular distance is 100 millimeters or 0.1 meters. Of course, this has a unit of newtons. And then I need to look at my horizontal force. My horizontal force, when I spin that clockwise, is going to go like this. And it's going to go tail first. Because it goes tail first, that means I subtract it. So I'm going to have minus 300 times the cosine of 25 times my perpendicular distance. Well, how far is this? This distance right here is 200 or 0.2 meters. Again, this has a unit of newtons. So my total moment is, I just need to get the calculator out. 300 times the sine of 25 times 0.1 minus 300 times the cosine of 25 times 0.2. And we get this is equal to minus 41.7 Newton meters. Okay, what this means is our assumption that clockwise was positive was incorrect. So the positive direction is really this counterclockwise direction. We can solve that. We can say, okay, this is really 41.7 Newton meters in this counterclockwise direction. All right, so now let's just say, oh, what if we had done this in the counterclockwise direction? What if we looked at the moment of D in this counterclockwise direction? So we're going to sum our forces about point D, And when we do that, let's look at this vertical force again. Well, again, let's move it up here, and we're going to be going this way. So we pin our problem about point D, and we spin the entire problem, and what we get is something like this. So we see that the tail is going to be going first. So we have to subtract. So we're going to have minus 300 times the sine of 25 times 0.1 meters. Again, this is a Newton. And then when we spin this 300 times the cosine of 25, and we're going to spin it in this direction, well, what happens, it's going to go, and it's going to spin head of the vector first. So that means we're going to add this vector. So we're going to say this is plus 300 times the cosine of 25. The perpendicular distance is still 0.2. And we can do that calculation. So let's minus this one and plus this one. And we get that this is equal to 41.7 Newton meters. A good check. Well, it's the same magnitude, but that negative sign, there's no negative sign out in front. So that means that this counterclockwise direction was correct. So we get the same answer regardless of if we sum our forces for the moment in the clockwise or the counterclockwise direction. All right, so now let's look at the second part, which is we want to determine the smallest force that we can apply at point B that creates the same moment, so that creates this 41.7 Newton meter moment at point D. Let's look at this from a geometric perspective for a minute. If I applied a completely vertical force, the perpendicular distance between this force and point D is going to be this distance of 200 millimeters. Similarly, if I applied a horizontal force at point B, this perpendicular distance is going to be, again, 200 millimeters. Now, if we look at the equation for a moment is equal to a force times a distance. Now let's look at what the question's asking. The question is saying, I want to minimize my force. So if I minimize my force, that means I'm going to have to maximize whatever my distance is to get this moment. So if this is minimum, this is going to have to be a maximum. Well, it turns out that to get the maximum lever arm, we need a perpendicular lever arm. That's going to be the longest distance that we can ever have. And this length is going to be equal to, well, we have a right triangle. So we're going to have the square root from Pythagorean theorem of 200 squared plus 200 squared. So my length is equal to 282.84 millimeters, which is equal to 0.28284 meters. So now we know what our moment is. We're trying to get the moment of 41.7 Newton meters. And we're looking for a force, but we know that the maximum distance we can have is 0.28284 meters. So now we can solve for my force, and the minimum force that I can have is going to be 41.7 divided by this 0.28284. And this force is going to be 147.4 newtons. So this means if I apply a force of 147.4 newtons at a 45-degree angle, this is going to be the minimum force that I can apply at point B to get a moment about point D that is 41.7 Newton meters.